We're just waiting to connect radio, and then this stream will be commenced. Hello people, this is VK3AML with the regular Saturday night transmission of stuff, a test transmission of material, which I guess keeps the airwaves with something that people can tune into, particularly during a lockdown and a pandemic. Although we've had less of that lockdown this week, thank goodness. Tonight chiefly, I'll be running videos related to modulated light communication, which over the years I've done with the late Tony 3AML, John Eggington VK3EGG, then 3ZGJ back in 1975 and 6, Clint Turner KA 2008 when I was in America, and early this year I see we're getting dropped frames too, so this is not a good start for the night. A lot of dropped frames. In fact, it looks like it's crashing for whatever reason best known to itself. I hope it settles down. So sometimes internet works very well and sometimes not so good. 658 dropped frames so far. Anyway, we'll be covering modulated light communication. Now, why modulated light? There are three reasons. One is privacy, because in a narrowly focused light beam you can maintain contact with the person that you intend the contact for, and the internet is dropping and recharging for some strange reason, and dropping again. I hope we can maintain the stream. Not good. Some weeks it works well, some weeks it works crap, and it's working crap at the moment. So I'll try and commentary on the video clips that you'll be seeing tonight via the YouTube live stream. If you want to look us up on YouTube, provided it works of course, look for VK3AML 31 July 2021, and we're switching on and off and on and off and losing stream like mad. But for the first clip I'll take you back 32 years to 1989. Now that was the first year that I built a full duplex portable light beam unit using then high output indicator LEDs of the 2000 millicandela type, and took two units around to Tony 3AML's place in Surrey Hills, and we got it working so far as it would, and set up a contact over about 1 kilometre. By the time we got the stuff operating, I had one station in Wattle Park in Surrey Hills, and the other station on Tony's roof where Tony was taking a video. What people made of me shining a red light outside the public lavatories in Wattle Park at 1 o'clock in the morning, I have no idea. But you'll hear the recording of that contact that Tony made on video in May 1989. So you'll see me with a lot more hair, and a lot darker hair too, and the late Tony Sanderson in control of the situation. So if you look in on VK3AML live stream 31 July 2021, you should be able to see this as well as hear it.
On the front it's got a couple of, what are they? Fresnel lenses. Well, I wonder if we'll see the lead there. Hang on.
And that is Tony.
Yes. There's something shining up there.
We'll just give it to you later. 1, 2, 3, 4, 5. That should have an interesting effect in the strobing actually. If my voice strobes with the scanning pattern.
Ooh, up and down. Anyway, what we can see there, we can see a site. Chris has built a site up out of bits and pieces there. Give us a look on the side of it. There it is. I wonder if we can see that site. Now there's the actual lead, if you can see it in the back there, glowing away. So that's what's making the light. There's the rest of the tronics.
There's the craphones on there.
And further up there we've got the site. There's the bits of site. And the
That's
front
a achromatic doublet, 2 inches diameter. It focuses onto this little crosshair, which is on a piece of glass just there on the focal plane, and that's the eyepiece, which just magnifies the image that's focused on that. So it's all very, very straightforward.
Now, as far as what's inside the actual device is concerned, what have we got? We've got a, is it a
You've
two?
got a 2000 millicandela lead there, so what you're seeing is only by backscatter inside the...
So that's a 2 candela device. Now, what have you done to that?
I've shaved the lens off it.
The convex front?
Yeah, the convex front's been shaved off, so it's just the chip inside showing.
Right.
And just in front of that, you can't see it, but it's inside. About, or I suppose, half a centimetre in front of that, there's quite a thick plano-convex lens.
Right.
Important point. That plano-convex lens, as far as I know, was the first time we'd used a dual lens optical system, and it worked extremely well to the extent that it's become a standard arrangement in light beam communication systems of this type. Anyway, back to the video.
Which regulates the dispersal of the light coming out of this and hitting the Fresnels in the front. So that the lens is designed so that the Fresnels in the front are just illuminated without losing too much off the sides.
We're now about to
Is that the right way up? No.
put one of the units up on the roof. Long doing ascend missions.
Okay, how about we head off to the park now and see how it's coming through down there. Over the shoulder and away we go. The receiver itself, the receiver and transmitter are standing, only about 2 feet high.
As you may gather from that voice, we now have contact with the Long.
Yeah. Hello.
Hello.
Yeah, actually, you're modulating a bit too much. The mic must be near the speaker.
No, I turned it up and I'm a mile away from the microphone, so I'll turn it down a bit.
Yeah, the speaker sounds louder than you, and when I speak, I can hear distortion.
Okay. No, you're not distorting.
If we can set this up properly, when you get your...
Hang on, we're about to run out of battery. Just stand.
Am I overulating?
No.
This is Chris Long speaking from Wattle Park on a modulated LED. And this is the first two-way communication by light beam that I've been able to set up for about 13 years since John Eggington and I had the Mercury arc system going. How are things at your end, Tone?
And when we think of we're still losing about 1 frame in 5 on the YouTube stream, so not going well. Can't know what I put that down to. Anyway, eventually, some 20 years later, in association by that time with Mike Groth in Hobart, and hello to Mike if you're watching, and with Clint Turner in KA7OEI in Salt Lake City, I assembled with the other two a presentation for an optical engineering conference in San Jose in Salt Lake City, and got myself a subsidized trip to California to present all of that. And with any luck, I'll be able to find the presentation that we gave, and here it is. Decibels versus dollars. Long-range atmospheric communications on a tight budget by Long.
This is a presentation by amateur radio operators. Radio hams. Our experiments are always self-funded and tightly budgeted. Our interest lies in exploring the range limits of terrestrial optical communication. To us, commercial viability, high reliability and broad bandwidth are secondary considerations. We do our experimenting inexpensively and hopefully have a little fun along the way. Our experiments began in the southeast of Australia. On February 19th, 2005, we set a world record for a two-way speech-modulated optical contact across the island of Tasmania.
time hath come, the war is said to speak of many things, of ships and shoes and sealing wax, of cabbages and kings.
I can hear you, I can hear you.
More recently, an associated group in Utah refined these techniques and confirmed their validity by setting a further world record of 278 kilometres between mountaintops in Utah. They did not use laser light, high power or expensive optics to do this, but they did span 2/3 of the state of Utah. Perhaps the first serious amateur radio contribution to optical communications was made by a team from the Electro-Optical Systems Amateur Radio Club of Pasadena. In 1963, just months after Bell Labs demonstrated the first visual output helium neon laser, the Electro-Optic Systems team transmitted a speech-modulated beam right across the Mojave Desert. The log tape of that transmission tells the story.
May 4th, 1963, the time approximately 21:32. This is W6POP operating portable from Grassy Hollow in the San Gabriel Mountains, running a test of a laser communication system over a distance of approximately 118 miles, with a radiated output power of 1/8 of a milliwatt at 115 microwatts. The transmitter uses a helium neon gas laser with confocal mirrors. The output is collimated using a 10-wire telescope. The laser is pumped and modulated using a Viking tube at 28.60 megacycles. The receiver is located at about 12 miles from Ballarat on a ridge in the Panamint Mountains. The receiver uses a 12.5-inch diameter telescope as main antenna. The received signals are modulated using an S20 photomultiplier tube and further amplified and fed into a loudspeaker and a recorder.
I'll just interrupt the stream there to say that I haven't updated the title of the stream, so it's actually coming up as 24 July 2021. So if you have any trouble finding me by looking up VK3AML 31 July 2021, try 24 July 2021, and if you get the Lightbeam stream, that'll be me. Back to the presentation. VK3 Alpha Mike Lima testing.
This may be the oldest sound recording to indicate the severity of fast fade or scintillation on a coherent beam sent through the atmosphere. If we lived in a vacuum, laser light would be ideal for communications, but in passing through moving air cells of differing temperature and density, coherent wave fronts randomly cancel and add. Scintillation, fast fade, is the major problem. Only optical fibre transmission can completely eliminate it. The 1963 Electro-Optic Systems test used a laser beam expander. By aperture averaging across the beam profile and straddling adjacent air turbulence cells, this expander reduced scintillation sufficiently to make their speech modulation intelligible. Unfortunately, large laser beam expanders have to be made with diffraction-limited precision optics, and they're very expensive. Here's Clint Turner's video comparing a laser beam with a light-emitting diode beam on a 24-kilometre atmospheric path. The camera is focused on the receiver's Cassegrain telescope mirror, 20 centimetres in diameter. With the laser, the speckle pattern is a chaos of deep rapid scintillation extending up into the kilohertz region. This laser beam has a minimal capacity to convey recoverable modulation. Now the beam from a light-emitting diode, expanded to 20 centimetre diameter by a collimating lens. The scintillation is slower and shallower, around 7 dB fades at 10 Hz. The beam's capacity to convey recoverable modulation is much greater than the laser, even if the beam flux is lower. Could it be that coherence is undesirable on atmospheric optical links? The physicist Albert Michelson indicated one cause of atmospheric scintillation way back in 1890. Light from a distant source, for example a star with an angular size less than some critical value, will exhibit local coherence, resulting in scintillation via interference. However, if we increase the space between the observing points, like this, to make the viewing aperture larger, the coherence will disappear and consequently atmospheric scintillation will fall. Large apertures mitigate scintillation. For a given aperture, shorter wavelengths also reduce local coherence, suggesting that visual wavelengths have at least one advantage over infrared for communications. Scintillation can also be reduced by using a thin diffusing filter to scramble a laser's phase coherence, reducing wavefront cancellations and signal dropouts. Korotkova, Andrews and Phillips recently indicated that partially coherent or even non-coherent beams would outperform lasers on atmospheric scintillation. The key to our success on long ranges lies in our elimination of beam coherence. John Gower's 1984 book, Optical Communication Systems, provides a first approximation formula for maximising the received optical signal. Received signal power ρ is proportional to the source radiance multiplied by the area of the transmitting lens multiplied by the area of the receiving lens. Our collaborator Mike Groth then adds a geometric correction factor G for the transmitting lens, which we'll explain shortly. This is all divided by the square of the distance between the stations, the inverse square law. Big lenses and intense light sources are essential. The geometric correction factor arises because as the transmitting collimator focal length is shortened, particularly below an F/D ratio of 1, the beam divergence increases at a greater rate than the total beam power. The geometric loss of a mirror is less than that of a lens of equivalent F/D ratio, as a parabolic mirror can surround an isotropic source, intercepting more of its flux than the flat plane of a thin lens. Intense, non-coherent sources for optical communication are improving rapidly. Standard light-emitting diodes have limited output as they don't provide, and their epoxy encapsulant can't withstand temperatures above 120 degrees Celsius. The new Philips Lumileds Luxion rearranges the whole light-emitting diode system. The emitting chip is mounted on a thick metal heatsink slug and it's surrounded by high-temperature silicone encapsulant. The red Luxion's chip is shaped like a truncated, inverted pyramid, its angled walls reflecting light forward by total internal reflection. Its efficiency and power handling capacity are both greater than standard light-emitting diodes by several orders of magnitude. They're available on a small star of metal-backed circuit board for easy attachment to a heatsink, the so-called Luxion star. The red Luxion is reputed to have a modulation bandwidth in the order of 10 MHz. Luxion 3 can be driven to unprecedented current densities, 1.5 amp continuous at 3 volt, into a chip less than 2 with a light conversion efficiency above 30%. A laser with hundreds of milliwatts of visual output would be prohibitively expensive and hazardous to use. A Luxion's output becomes eye-safe after beam expansion via a Fresnel lens, as this greatly reduces the beam flux density. A collimator of very large aperture need not be expensive. Acrylic Fresnel lenses are reproduced by moulding like vinyl LP records, and they're available in apertures up to about 1 square metre. They're much lighter, cheaper and more robust than glass collimators of similar aperture. And modern Fresnels avoid spherical aberration, an effect present in all spherical surface glass lenses. This is caused by rays from the outer parts of the lens having a shorter focal length than rays concentrated near the lens centre. The Fresnel is a near-ideal collimator for optical communications, but moulding inaccuracies restrict them to use with non-coherent sources, as they're not diffraction limited. They're offered with groove pitches ranging from 0.12mm, the finer pitch producing more image definition, but greater lens transmission losses. So, how fine can the image be with Fresnels currently available? This is the star Vega, imaged against a 1mm scale by 4 modern Fresnel lenses between 25 and 40cm square aperture. The Fresnel focal length is shortest at the top left, longest at the lower right. The image spot diameter increases with the focal length, ranging from 0.1mm for the shortest lens to 0.45mm for the longest. These collimators are all adequate for our purposes, with blur circles much smaller than the source chip of Luxian light-emitting diodes and smaller than the sensitive area of most photodiodes. So, how do we optically couple the Luxian to the Fresnel collimator? The Luxian is supposed to have a radiation pattern following the cosine of the radiation angle, a Lambertian pattern. In practice, the red Luxian chip's truncated pyramid more typically radiates in this way, more broadly than the Lambertian model. Rotating this radiation pattern 90 degrees, the ray diagram of a Fresnel lens with an F-on-D ratio of 1, we see that the Luxian couples fairly well into its collimator. But the Fresnel lens only intercepts the shaded part of the Luxian's radiation pattern, about 35% of the total flux. This loss can be offset optically, as we shall see. A standard Fresnel collimator produces a beam divergence angle θ dependent on the diameter of the light source and the focal length of the collimator. When a source is too small to fill the Fresnel's blur circle, a plano-convex secondary lens of high diopter allows adjustment of the virtual source size to maximise the far-field intensity of the beam. With a Luxian large enough to already fill the blur circle, the secondary lens can make greater usage of peripheral emission from the light-emitting diode. We've found that by adjusting the relative focal lengths A and B, we can optimise the far-field beam intensity, or at least increase the beam divergence angle without losing beam intensity. The secondary lens can be very simply mounted above the Luxian with 2 bolts through the heatsink, providing a height adjustment. Our standard rigid optical housing, shaped like a truncated pyramid, places the transmitter and receiver Fresnels side by side, providing full duplex operation, continuous transmission and simultaneous reception. Plywood or fiberglass construction retains heat after sunset via thermal insulation, avoiding dewing. A photographic tripod and a rifle sight are sufficient to align the unit with the distant station. The optical housing need not be rigid. A very light transceiver, conveniently folding flat for transport, could be constructed by hinging the Fresnels to their central baffle and by using a cloth bellows over receiver optics. Our transceivers produce a beam of around 4 to 10 milliradians divergence. VK3AML's unit throws a spot on a distant tree, a spot about a quarter the width of the full moon. And looking back into the beam of even a small Luxian Fresnel combination, the light is clearly visible to immense distances, more than 60 kilometres in this case. Silicon PIN diodes are small, very cheap, this one retails for less than $2 and extremely sensitive. These simple devices have a fairly high junction capacitance, which can limit their response speed unless they work into a suitable low impedance, low noise preamplifier. The standard arrangement is to back-bias the photodiode and to have it working into a trans-impedance amplifier. That is, an amplifier presenting the diode with a very high DC resistance, but by the use of a feedback resistor, a low AC input impedance. This circuit is a photocurrent to voltage converter. During the day, ambient light can cause a photodiode DC offset, which can bias the amplifier to cut off. This DC must be blocked by using an extra resistor, which unfortunately lowers the signal-to-noise ratio. Now, this circuit is great when a megahertz or more of bandwidth is needed, but when you're breaking record BPW34 photodiode, for example, this results in a 6 dB per octave high-frequency roll-off above 200 Hz. There are ways to compensate for that, exemplified by some rather cunning improvements devised by Clint Turner of station KA7OEI. John Ureck's basic concept of feeding the photodiode into the open-circuited gate of the FET is retained. But Turner adds extra backbias to the photodiode through this voltage divider, reducing the detector's shunt capacitance and increasing its quantum efficiency. A constant current source transistor applies fairly high standing current to the FET, but simultaneously presents the FET drain with a high AC impedance. The high standing current maximises the FET's transconductance and thereby increases the circuit's signal-to-noise ratio. The second half of the cascode amplifier in this arrangement is a grounded base transistor stage, resisting voltage changes on the FET's drain and minimising the effect of the millicapacitance between the FET drain and the photodiode. This also adds a little bit of gain to the system. Finally, a low-noise 6 dB per octave high-frequency boosting circuit compensates for the shunt capacitance across the photodiode, extending the bandwidth to 10 kHz or more. This circuit has been measured to have 12 to 20 dB greater signal-to-noise ratio than the best transconductance circuit that we've been able to construct. Construction of this circuit is quite straightforward, the only constructional quirk being in the vicinity of the input. Where the photodiode connects with the gate of the FET, the extremely high impedance connection must be in air, not on the circuit board, with the wires all kept short as possible. The Utah group has already sent these slow-scan TV pictures over a 172 kilometre atmospheric optical link in September 2007. Standard fast-scan TV could also be transmitted with only a few circuit changes. So now we look towards one of the world's longest line-of-sight paths, Mount Ellen in southern Utah to Uncompahgre Peak in Colorado, just less than 300 kilometres, across high, dry, largely uninhabited country near the headwaters of the Colorado River. On the summit of Mount Ellen, this pit is a remnant of an earlier world record for optical communication, set with an early technology on the 17th of September 1894. That was when the US Army Corps of Signal Sergeants sent the longest ever optical Morse communication to Uncompahgre Peak via articulated heliograph mirrors. 114 years later, we plan to span this historic test range again, this time with audio and video. But we'll do it inexpensively, without lasers, and avoiding optical coherence. Thank you so much for attending this lecture, and we'll field some questions as soon as the end credits conclude.
Well, that was presented at the SPIE Photonics West conference in 2008, when I was over in America, and we aimed it at an audience that knew a little about electronics and a lot about optics. But for those who are interested just in the usage of this equipment, Clint Turner, KA70EI, when I got to Salt Lake City to meet him and the optical communications group there, after leaving San Francisco by train, suggested that we should go down to Southern California to meet one of the pioneers of optical communication there. Back in 1963, Bob Legg, W6QYY, who was in 2008 when we met him, was 84 years old, had been involved with actually building one of the first privately owned gas lasers. And they put a modulator on it in 1963 and managed to transmit the laser beam with audio right across California, a distance of 118 miles, as I mentioned earlier in that presentation. Well, Clint and I went by car over a few days down to Southern California from Salt Lake City, and Clint brought his optical communication system equipment, very similar to mine, down there, and we did a demonstration for Bob between hills in the Yucca Valley area, which is near Death Valley. So hopefully I'll be able to show you the video that we recorded at that time. Clint Turner, KA70EI, driving the car, myself doing the commentary, and you'll see us doing a test in Southern California. So this is the first W6 to VK light, pardon me, bad cold, light beam contact.
Clint, who's driving the car. Say hello to Australia, Clint. Hello. Don't keep your head on the wheel. Out beyond him is the Mojave Desert out there, which is a pretty large amount of nothing.
There's sagebrush and trees.
Yes, more trees, sand, salt pans. Around to the right, the mountains are San Bernardino Mountains. So there apparently are houses out here, but God knows what sort of person lives in houses like these. Hopefully Yucca Valley will be a little bit more civilized. This is around 10:20 a.m. on Saturday the 2nd of February.
And this is W6QYY, Bob Legg, a NASA pioneer as well as optical communication pioneer. We met up at his house. He put us up for a couple of days, which was really nice of him. And that's him with his partner Beverly and their dog Carlos.
In 1 hour time, my sensor inside said we had 15 inches of rain in the last hour.
But you knew that wasn't true because your house was still here. We hope you come.
Well, if it's practical to get up line of sight up there, then set up on anywhere along here.
We were trying to decide which hillock we were going to set up our gear on. Bob knew which hillock had the tracks going up them that they could take the car up with the gear.
Whatever you think is more practical. It'd be fun to go on this, but that's not practical.
In that afternoon, we saw quite a few roadrunners and coyotes as well.
Yeah, I don't know how practical that one is. I mean, at that distance you'd get some scintillation, which is interesting in itself. But.
Well, if we took off now...
Okay, it's near sunset, and here comes Clint with a box of tricks.
That's his optical communication unit.
Apparently for Bob's benefit and to try and have the first VK3AML light beam contact. This is Yucca Valley. We're on top of a kind of a knob up here. You can see Clint's taking infinite dangers, putting his gear on top of a very rickety rock. A rickety rock. Whoa!
There we go, that's not too bad there.
And for the first time in my life, I'm having to dodge cacti.
Okay.
This is desert country.
Alright, that should work.
Okay. You're going to take your digital audio recorder with you to do a bit of logging?
Yeah, in fact, I'll leave one with you and show you how to run it.
Okay. Ooh.
So we'll have two-way full transmit and receive logging.
You're going to leave that on audio transmit? And whereabouts are you going to head? Somewhere up in those piles of rock up there?
I believe I see a road. See that tower up there? On the bottom of the hill, I see a road. All we need to do is get over there to the bottom of the hill.
All right.
That should be line of sight.
Yeah, well, down the bottom there you should be in slightly better temperatures than up on top.
Well, we only need to go up high enough to see this place.
Yeah. Oh, that's interesting. There's a flashing light over on that tower over there.
We have a moment to come back and I'll show you how to run the audio.
Okay. Let's have a close look at this. There's the light beam transmitter. One of the smaller ones. And their house is back over here, so I'll dodge through all of the cacti. Just hope to God there are no snakes or scorpions or whatever it is they have in the Mojave Desert here. Dear, dear, dear. This is the evening of Saturday the 2nd of February, and this is Bob Legg's place up here, out in the scrub, desert, whatever. We've been watching road runners come up here earlier in the day. So this is the back of Bob Legg's. And I better close this in case. There we go.
Okay, there's the audio. Here's the little audio recorder.
Alright.
This is the power switch.
I'm going to switch off the video so I can see this being done.
Alright.
Okay, and we're aiming up in...
off at the moment.
We're aiming up in that direction towards the saddle that you see. Yeah. So this is preliminaries to a test of light beam over about, I'd say, a 10 mile, maybe 15 course.
Later that